Fiber-reinforced concrete is a concrete characterized by a significant toughness, able to guarantee residual strength after cracking due to the presence of random fibers made of different materials dispersed in the concrete matrix. Although it was introduced in the first 60s of the last century, it was investigated for a long time because it requires fracture mechanical theoretical principles. Moreover, only in the 90s the chemistry allowed to achieve a mixed design with a significant amount of fibers without preventing the casting due to the workability reduction associated with the fiber introduction. FRC is a very effective material to retrofit existing structures made of concrete. Let we see the jacketing of a pier basis and the repairing of a bridge top slab against chlorides attacks. In the market, many types of fiber are available. It is possible to split the fiber world in two large categories, the metallic and the synthetic fibers. The former are the most used until now to guarantee high performance of fiber-reinforced concrete and can be split into three classes according to the equivalent diameter of their cross-section. Macrofibers, with a diameter in the range of 0.8 to 1.2 mm, mesofibers in the range of 0.5–0.8 mm, and microfibers in the range of 0.15–0.5 mm. It is worth to note that synthetic fibers can reach a minimum diameter in the order of 10 microns. The strengths characterizing the three steel classes are aligned to the values of conventional rebars, D-Widam bars, and steel used for pre- or post-tensioning. Looking to the most used steel fibers, the structural effectiveness is guaranteed only if fibers are well dispersed in the volume. If fibers are concentrated, no local toughness is achieved. Obviously, for example, an amount of 40 kilograms of fiber in a cubic meter of concrete corresponds to a growing number of fibers depending on fiber sizes. We can count around 160,000 fibers up to a total number of around 20 millions, passing from macrofibers 60 mm long with a diameter of 0.8 mm to microfibers 13 mm long with a diameter of only 0.16 mm. The residual strength after cracking is due to the bond between the fiber and the matrix in the pull-out action. Even if we adopt a straight fiber embedded in the same concrete mix, the residual strength shows a certain scatter due to the distribution of aggregates around the fiber. The high standard deviation in the response is one of the peculiarities that has made difficult the evaluation of the fiber residual strength in the post-cracking. In a uniaxial tension test carried out on a notched cylindrical specimen, fiber pull-out contribution corresponds to the Q after the crack opening. Only the accumulation of fiber pull-out resistant mechanism can give a significant contribution to the overall response after cracking. Fiber-reinforced concrete performance in bending is measured by means of a 550 × 150 square mm notched prismatic specimen to reproduce a third point bending test. Three parameters qualify the mechanical response of the material: the limit of proportionality FRK, the serviceability flexural strength FR1K associated to a crack opening of 0.5 mm, and the ultimate flexural strength FR3K associated to a crack opening of 2.5 mm. In particular, the FR1K value and a letter in the range AE used to recognize the ultimate residual strength versus serviceability strength ratio classifies the mechanical behavior of the material. Starting from the classification, it is possible to identify, by means of equilibrium equations, the pull-out resistance offered by fibers in a uniaxial tension and the constitutive law in uniaxial compression. According to the amount of fibers and to their effectiveness in the matrix, mainly depending on their aspect ratio, corresponding to the ratio between the fiber length and its equivalent diameter, their geometry, and the bond strength of the matrix, it is possible to obtain two main behaviors in uniaxial tension: a softening behavior characterized by only one crack formed in the weakest cross-section, or a hardening behavior with a second branch along with a progressive microcrack propagation takes place until a crack localizes and the following softening behavior takes place. The hardening materials today available in the market represents the most significant product obtained by the advanced products made available by chemistry in the 90s. Only concrete in the last decades has been able to improve so much its compressive strength, reaching strengths comparable with steel at a much lower cost. This research conquest is due to the possibility to compact the constituent of the conglomerate by adding to the traditional elements, aggregate, cement and water, also superplasticizers and other very fine constituents like silica fume, blast furnace slag, quartz powder and fibers, thus reducing the water-cement ratio. Analyzing a common mix design of this product, it is possible to observe that the percentage of cement is very high with respect to a traditional concrete. We know that 1 kilogram of cement corresponds to around 1 kilogram of CO2 emission in the atmosphere. This means that to obtain a sustainable material, a reduction at 1/3 of the volume needed for a conventional concrete element must be obtained in the structural design when this type of material is adopted. The quality of the surface and the very low porosity guarantee also a much higher durability of the material in the time. A comparison in terms of equal bending strength is shown with reference to a wall thickness. An example of bearing capacity in bending is also shown to highlight the impressive resistance of this material before cracking. The high strength in compression and in tension can allow an impressive increase even of the domain Mn, bending moment axial force, of a column by using the jacketing technique, represented by a reduced thickness of only 40 mm. Let me show now few examples of application. HPFRC can be used to repair top slabs of a bridge deck by using the high bond between the concrete support and the fine matrix of HPFRC and its very low porosity. The HPFRC can be also conventionally reinforced in case of significant thickness. Always in the bridge structural retrofitting, HPFRC can be useful in the joints because its higher bond strength can reduce the sizes of the joints. In the bridge structure, the jacketing technique can be very effective also to strengthen piers, guaranteeing a high durability in the time. Special solutions to improve shear capacity have been already proposed in Germany, allowing a fast and economic solution that could be temporary or definitive according to a specific design. At Politecnico di Milano, my research team is investigating other solutions to strengthen half joints. The idea is that to couple a HPFRC reinforced top slab to the original dapped end to detect the damage in the half joint and, at the same time, to increase its bearing capacity.